Hello everyone, this is Sanjeevani Rai, roll number 21NS0-162. I would like to present a presentation on plasma diagnostics using Langmuir method. Let's see what a plasma is. A plasma was first identified in laboratory by Sir William Crookes. Crookes presented a lecture on what he called radiant matter to the British Association for the Advancement of Science in Sheffield on Friday, 22nd August 1879. Plasma is one of the four fundamental states of matter. It contains a significant portion of charged particles, ions, and/or electrons. The presence of these charged particles is what primarily sets plasma apart from the other fundamental states of matter. It is the most abundant form of ordinary matter in the universe, being mostly associated with stars, including the Sun. Plasma is called the fourth state of matter after solid, liquid, and gas. It is a state of matter in which an ionized substance becomes highly electrically conductive to the point that long-range electric and magnetic fields dominate its behavior. Now, moving to plasma diagnostics. Plasma diagnostics are a pool of methods, instruments, and experimental techniques used to measure properties of a plasma, such as plasma components, density, distribution function over energy, temperature, the spatial profiles, and dynamics, which enable to derive plasma parameters. Plasma parameters define various characteristics of a plasma, an electrically conductive collection of charged particles that responds collectively to electromagnetic forces. Plasma typically takes the form of neutral gas like clouds or charged ion beams, but may also include like dust and grains. For methods, we have the invasive probe methods, ball pen probe, Faraday cup, Langmuir probe, magnetic B-dot probe, energy analyzer, proton radiography, self-excited electron plasma resonance spectroscopy. Out of these, we're going to discuss the Langmuir probe. Measurements with electric probes called Langmuir probes are the oldest and most often used procedures for low temperature plasmas. The method was developed by Erwin Langmuir and his co-workers in the 1920s and has since been further developed in order to extend its applicability to more general conditions than those pursued by Langmuir. Langmuir probe measurements are based on the estimation of current versus voltage characteristics of a circuit consisting of two metallic electrodes that are both immersed in the plasma under study. The two cases are of interest. The surface area of the two electrodes differ by several orders of magnitude. This is known as the single probe method. The surface area is very small in comparison with the dimension of the vessel containing the plasma and approximately equal to each other. This is the double probe method. Conventional Langmuir probe theory assumes collisionless movement of charge carriers in the space change sheath around the probe. Further, it is assumed that the sheath boundary is well defined and that beyond this boundary, the plasma is completely undisturbed by the presence of the probe. This means that the electric field caused by the difference between the potential of the probe and the plasma potential at the place where the probe is located is limited to the volume inside the probe sheath boundary. The general theoretical description of a Langmuir probe measurements require the simultaneous solution of the Poisson equation, the collision-free Boltzmann equation or Valsov equation, and the continuity equation with regard to the boundary condition at the probe surface, and requiring that at large distance from the probe the solution approaches that expected is an undisturbed plasma. The Langmuir probe. A Langmuir probe is a device used to determine the electron temperature, electron density, and electrical potential of a plasma. It works by inserting one or more electrodes into a plasma with a constant or time-varying electric potential between the various electrodes or between them and the surrounding vessel. The measured currents and the potential in this system allow the determination of the physical properties of the plasma. Now let's look at the Langmuir probe, the electrostatic probe. It is a metal wire placed in a plasma to measure current and voltage. We have a metal chamber with a plasma generated inside it. We insert in this metal chamber a very small wire called the Langmuir probe. We attach it to the power supply, which applies a voltage between the probe and the body of the chamber. The Langmuir probe enables the plasma temperature and the electron ion densities to be measured. Let's see the plot, where V is the applied voltage, I is the current. Here is the ion saturation current, which is highly nonlinear curve, as we can see, and it allows the density of the ions to be determined. Vf is the floating potential, where electron and ion current are equal, therefore no net current to the probe. Vs is the plasma potential before electron saturation current region. It enables the electron density to be enabled. Let's now move to electron saturation region. Let's imagine we have a plasma. Then we introduce a Langmuir probe and a very large positive voltage on it with respect to the chamber walls. As a result, electrons are attracted to the probe and form a negative space charge region, which is a negative sheath. The ion saturation region. We replace the probe tip in the plasma and apply a large negative voltage. Ions attract to it and thus form a positive space charge or a positive sheath. Let's obtain the ion density of the plasma from ion saturation current. The expression for current density is this, where Ji is the ion current density, I is ion current, and A is the surface area of the probe. We can also write the current density as this, where Ns is the ion density at sheath edge and B is the Bohm's speed, which is also this. We can write the ion current as follows. It only includes the current density at the sheath edge, but we need the density in the main body of the plasma. Using the Boltzmann relation, we see that this is the potential at sheath edge and NOE is the plasma density that we want. Potential at sheath edge is defined to be the following. Now substituting into the Boltzmann relation gives the following. And then we get the value of Ns as 0.61. And if we round down, the value will be 0.5. Now the ion current becomes this, where Ns has been replaced by 0.5. Now to calculate the electron density, we have to know the electron temperature, which is unknown to us. Therefore, we need to measure the electron temperature T. Now let's recall the diagram that we had seen. We notice new components, the two resistors in the plasma with voltage Vp and Vs across them. There are no resistors in the plasma, but the plasma does not depend on the resistance. The Vp here is the voltage between probe tip and plasma. Vs is the voltage between plasma and the walls of the chamber, known as the plasma potential. As we all know that from one of the Kirchhoff's law, V is equals to Vp plus Vs. We will need this to find out the plasma density as determined from the electron saturation current. Let us obtain the electron temperature. Let us assume a probe tip as planar, that is, electron drift speed moves along the x-axis. The electron density is given by this expression, where f is the distribution function, or f is the Maxwellian distribution function. Vt is the speed of the electron that reaches the probe tip. The energy of these electrons have to overcome the potential difference Vp. Therefore, the kinetic energy is given by this. Now, substituting Vt and carrying out the integral, we finally obtain the expression for current given by this. We then obtain the electron temperature in the IV curve. By taking the natural logarithm of both sides, we can obtain the electron temperature by this equation. The electron temperature can be taken from the slope of the line, but it has to be in this region of the IV curve between the flotation potential and the plasma potential. We now use V equals to Vp plus Vs in this, and we obtain the following. And at the plasma potential, we know that V equals to Vs, and the electron current is this. And as we know the current saturation current, we can obtain the plasma density.